Hello, friends. It is Ben again. This is a video for vector calc. No, it's not vector calculus. It's differential calculus. That's right. What we'll be taking a look at is linear approximations and then making the jump across to looking at local maximums, local minimums, otherwise known as local extrema. I would, yeah. To be honest, the linear approximation stuff is something that we need to talk about because it fits in with something else you might possibly come across later on, maybe not. But we don't spend a lot of time on it because the actual application end of it just isn't as important as it was, say, 50 years ago. So the notion, though, about the maximums and minimums, that portion is still conceptually important because it goes into this notion of trying to optimize things. And by optimize, I, of course, mean finding a maximum, finding a minimum. So let's take a look, and I am going to bring up something on the iPad. All right, so for our linear approximations, the super basic notion is that when you've got a function that's pretty smooth, okay, it's not all jagged or something, then when you are near a given point on the graph, if you make a tangent line, the tangent line is pretty close to the graph. It's that simple. That's what the idea of this is. Tangent lines are pretty close to the graph, okay? So if that's the case, then you can talk about figuring out the slope of this line. And if you multiply the slope by a little change in x, then the little change in y value should be the slope times that change in x. So the change in going up here on our function should be approximated by taking that tangent line change, and it's not going to be perfect, okay? But we get it by evaluating f prime at our point of tangency and multiplying by our change in x, okay? The general use that we put these to is when we're approximating something that we can't just directly measure or directly calculate. So the process you'll actually go through here is to figure out what your x sub naught is so that both your function and your derivative are easy to evaluate. And once you have that, you're going to evaluate the function and the derivative. And then the df that we talk about there, you're going to add it onto the function value at the point of tangency in order to approximate what this f of x naught plus delta x is, okay? Shouldn't be super rough. So we'll start out with a classic sort of problem here that asks us to approximate the square root of 15. So purposely, I've thrown you in here and we have to figure out all the pieces. The first piece to figure out is what's the damn function? You know, they did not write a formula for us for our function. We see we're talking about taking the square root of 15. Okay, so we make this guess square root of x. All right, now you have a square root button on your calculator. Your calculator can do a much better approximation than what we're asking you to do here. The purpose is not to know what the square root of 15 is. I also have a square root button on my calculator. If that's what I wanted to know, I would hit the button. What I want to know is if you can apply this process, okay? So here in this, you've got to think about both the f and the f prime are going to have a square root in them. I have to be able to plug in x values that I can take the square root of in my head. So we are going to think about what x values that are close to 15 have a square root that you could do in your head. I hope you're seeing that x naught ought to be 16, because the square root of 16 is 4. You can do that without any effort, right? So now to continue on here, we're going to have to figure out f prime of x. Remember that square root of x is really x to the 1/2 power. So the derivative is 1/2 x to the minus 1/2 power, or in other words, 1 over 2 square roots of x. So when you make use of our 16 here, maybe I'll put that over here, you will find f of 16, the square root of 16 is 4. And f prime of 16 is 1 over 2 square roots of 16, so it's 1/8. So the df in that formula is going to be that f prime, the 1/8, times, what do you have to do to change your x naught of 16 into a 15? You have to subtract 1. So the dx is minus 1. So this is f prime of x naught, and this is change in x. All right, so out of that we get minus 1/8. So here we'll find that f of 16 minus 1 should be approximately f of 16 plus the df. So that is 4 minus 1/8. So if decimals are more your speed, then you'd say 3 point, what is that, 8, gosh, embarrassingly, 4 minus 1/8. Embarrassingly, I could not do that in my head. So 3.875. Now, I am going to grab a calculator, and when I use a calculator to approximate it, I get 3.872983346. So there's a lot more digits to it, but it agreed up until the second digit. The third digit was where it started to go awry. So back in the day when people didn't carry calculators around, believe it or not, this was how you would approximate a square root, just by going through this kind of procedure here. So that's what's going on with this. It is old-fashioned technology stuff, and it's not super useful in that case, you know, but the process figures into something that you might end up doing later. All right, so here we're going to approximate the tangent of 47 degrees. Now, if you have never done sines, cosines, and tangents, you're in trouble. But also, if you've only ever done them by punching into a calculator, this may be a little bit of a problem. So what you need to spot here is that the x naught that's close to it, the special angle, is going to be 45 degrees. We know that the tangent of 45 degrees is 1, and the sine and cosine are 1 over the square root of 2. So we're going to take advantage of that. But you also are going to have to know that this is in radians. All of the calculus stuff about trig functions is always in radians. So now the other thing we have to think about is, what is our function? And it is going to be tangent x. And that tells us that the g prime should be secant squared of x. And so we can also plug into these fairly easily. So now we have to think about, what is the delta x? Now you can see that going from 45 to 47, we had to go up 2 degrees. But then we have to change that into radians. So multiply by pi over 180, and you end up with pi divided by 90. So here, when we talk about the dg, it's just g prime evaluated at your 45 degrees, or your pi over 4. And so that is secant squared of pi over 4. Secant is 1 over cosine, so this is really 1 over 1 over, oh gosh, so 1 over square root of 2, and then square it. So you ended up with a 2 here, okay? So then, I forgot to write down my delta x here. My delta x we said was pi over 90. So 2 times pi over 90 is pi over 45. If you'd like a decimal for that, we can certainly get it. But now we say tangent of 47 degrees is approximately the tangent of 45 degrees plus this dg. So the tangent of 45 degrees is 1 plus this pi over 45. And if you'd like an approximation, it'll take me just a second here, I get 1.0698. And you can carry on with that for more digits if you'd like to. But if I, on the other hand, ask the calculator to give me this tangent of 47 degrees, it gets 1.0724. Okay, so not super accurate there, but it gets us an approximation. So remember that the main thing in this is that dg is coming from multiplying your derivative there, okay? All right, so this one is a trickier bit. So we've got a machinist here. They're measuring a cylinder to have a radius of 1.2 centimeters and a height of 4.3 centimeters. And they know from working with their machining tools, their micrometers, their calipers, that they're going to get an error sometimes, but they're able to control the error, and they know that it's no more than 0.04 centimeters. So we're asked to figure out what the relative error is on this. So what we have to do is to think about our volume is pi r squared h, and then the change in volume that you get from changing the r and the h is going to be, now we have to think about going along with a chain rule sort of thing and a product rule. So pi times, we'll take the derivative of r squared, 2r, and then we'll write down dr, and we'll leave an h after it. Plus r squared, and then a dh. So the dr and the dh are going to be the plus or minuses there. Now, the thing that is, you have no idea what the actual error is. We're just looking at the worst case scenario. It could be that you overmeasure the height and undermeasure the radius, and somehow it magically cancels out. So all we're doing here is figuring out the maximum relative error. So for our purposes, we're going to come along here and put the pi and the 2 times, what did it say the r was? 1.2. And then it said the dr was at most 0.04. And then the height was 4.3 plus, and now we'll have the r squared. So 1.2 squared times the dh was at most 0.04. And so what we get out of this is going to be something I have to do in the calculator. 0.04 times 4.3 plus 2 squared. All right. I'm getting out of this 1.4778, and that's going to be in cubic centimeters, right? But now the trick comes in. What did I say in this? Not the error or even the maximum error, which is what we're really thinking about, but the relative error. Another phrasing for this could be that it's the propagated error. So if you're doing that, it is the error relative to the measurement. So our relative error is going to be this 1.4778. Hopefully you did not clear that from your calculator. Now we'll just divide it by the 19.4. Yeah, 19.4. And probably I should have had more digits of that. But when I do this, I get 0.07618. Okay. So when reporting that, I would refer to a 7.6% relative error. Okay. This sort of thing comes up sometimes, that you're asked to report a relative error when you're doing some kind of a process. So I wanted to try to make sure and work that into what we're doing. All right, our next bit here is what we refer to as finding a local extrema. So all we mean by local extrema is something like this on a graph, that you have the top of a bump or you have the bottom of a bump, bottom of a valley. Maybe I should say tops of hills and bottoms of valleys. Now, please realize that it may be the case that this local extrema is not the biggest extreme. I could certainly draw a quick function here, that has a local maximum, and that when you get far enough away, that you get something that's much more than that. But local maximums just mean that for other x values that are close to that particular value, that you have this being, your maximum. Okay. So your procedure that you're going to have for these sorts of things is that you find f prime, set it equal to 0, and solve for x. That gets you a critical point. Now, you might also have that something like this happens, where instead of having the f prime be equal to 0, it could be undefined, So some sort of division by 0 error comes up. But in either case, once you do this, you're going to get these x values, and you're going to test f prime to the left and the right of this, much like you did when you were finding intervals where something increased and decreased. So let's tackle these, right? So this first one here, we're going to find and classify the critical points, and it's just a polynomial. And I should probably turn it on to something where we can actually see it. So our f prime of x here can just be 24x squared minus 2x. All right, that's not undefined. So we're going to find our critical points by setting this equal to 0. You can see that 2x will factor out of that, and then you'll have 12x minus 1. Okay. And then the x values we get are x equals 0 and x equals 1/12. I purposely did this for our example here. Notice that the x values are super close to each other. Because of the fact that they're super close to each other, if you graph this, you will think that there's only one of them. It looks like there's only one of them unless you zoom in a lot on your graph. And you wouldn't know to zoom in, So, all right. So the notion that we're going to have in mind is that you get a number line, and 0 and 1/12 are the numbers that that are our cutoffs. And we need to test something that's a little bit less than 0. Actually, it can be a lot less than 0. Okay. And we need to test something in between. So I'm going to say 0.05. That'll be somewhere in there. And then test something that's larger. 1 seems like a good value. Okay. Why did I choose those values? They're all easy to plug into the calculator or to do by hand. So I am going to find f prime of -1. And all I have to do is to plug back into this here, right? So f prime of -1 is 24 times -1 squared, so 24 times 1, minus 2 times the -1, so it's 26. That means it's positive. Then I'm going to check f prime at 0.05. A little bit harder. So 24 times 0.05 squared minus 2 times 0.05. I cannot do that in my head, so I'm going to grab a calculator. 24 times 0.05 squared minus 2 times 0.05. And I got negative 0.04. That is negative. So this says that x equals 0 is a local, it's either a maximum or minimum. It changed from going up, it was increasing, to going down, and is decreasing. So this is a local maximum. Okay, so think of it as doing something like that. It was going up, then it started going down, so it's a maximum. All right. Then we knew that f prime at 0.05 turned out to be negative 0.04, which is negative, you know. And then we're going to check f prime at 1. And that's going to be 24 minus 2 is 22, which is positive. So that means it was going down and it changed to going up. So x equals 1/12 is a local minimum. I guess I should have spelled out maximum as well. All right. So that's the sort of thing we do here. This is referred to as the first derivative test. You're using the first derivative in it. As you might guess, there is a second derivative test, but that comes later. All right. Let's tackle another one. So with this one, we're going to take our g prime of x. Oh, actually, before we do anything, we ought to spot something here. What x values are you allowed to plug in? X has to be greater than or equal to -1. If you plug in numbers that are lower than -1, you'll be taking a square root of a negative. So look out for that. All right, g prime will have 1 minus 4 times. That square root is really a 1/2 power. So 1/2 of x plus 1 to the minus 1/2 power. And then the chain rule says we have to take the derivative of what's inside, but that's just 1. So we'll have this is equal to 1 minus 2 times 1 over the square root. I guess it would make more sense to put that as 2 over the square root of x plus 1. Okay. Now, look at it. Notice there's a division by 0 when x is equal to -1. So x equals -1 is a critical point. So we'll have to think about that a little bit, okay? But then we also have to think about, well, let me move that out of my way. And we'll have to set this equal to 0 and see what happens. And that would mean that we have 1 being equal to 2 over the square root of x plus 1. And you cross multiply, and the square root of x plus 1 equal 2. And that would say that you need x plus 1 to be 4, which is saying that x needs to be equal to 3. So these are our 2 critical points. So we think about our number line here. The one that's farthest to the left is -1. One that's farthest to the right is a 3. And we know that we cannot plug in any values that are less than -1. So we can't actually pick out any values that are over here. But we can pick out 0 in here, and we can pick out, say, 4 in there. And I'm just picking out numbers that are relatively easy to plug in. All right, I'm going to grab some of my work and push it over to the side, just so we have more room to write here. So we will go ahead and say f prime of 0 and plug, oh, I said f prime, I meant g prime, sorry, g prime of 0. So we plug in and have 1 minus 2 over a square root of 0 plus 1. So we end up with 1 minus 2 is -1, and that's less than 0, okay? So that says that if we were looking at the shape of this graph, it's not defined to the left of -1, but it's going down to the right. So x equals -1 is a local maximum, because all the valid x values that are close to it are going to turn out to be less, okay, or are going to give you g values that are less. Now we're going to check g prime of 4. So g prime of 4, you have 1 minus 2 over the square root of 4 plus 1. Man, I can't do that in my head either. So 1 minus 2 divided by the square root of 5. I get about 0.106. What's important is that it's positive, and we knew that the other part, we had something negative. So I'll move that down a little bit there and say that our g prime of 0 is equal to -1, which is negative. And then I can move this stuff back up here. And that tells me that x equals 3, that breaking point, is a local what? Well, it was going down, and then it changed and started going up. So that means that it is a local minimum. Okay, that's what you have to do on these. So this one was a little bit tricky because of the fact that we had a critical point that was at the end of the domain, and that caused us to have to do something up here that sort of broke the pattern. Okay. All right, and let's take a look at another one. Now this has ln of x. So we're going to come along here and find our h prime of x. And because it says ln of x divided by x, we have to use the quotient rule. So 1 over x is the derivative of log, and then the bottom was x, minus, and now we'll leave the ln x alone and take the derivative of the bottom, which is x, so we just get a 1 there. All that divided by, man, I'm supposed to straighten the line out. Okay, the bottom squared. So if you simplify that where it's easier to work with, it'll look like so. So you take a look there and you'd spot that you could have the denominator equal to 0, right? That would give you a 0 division error. But because of the fact that we're dealing with log x divided by x, we didn't have 0 in the domain. So we don't have to worry about that particular thing this time. So the other way of getting critical points is to have this equal to 0. If you have a fraction equal to 0, it had to be the numerator that made it 0. 1 minus log x is 0. that says log x is 1, and that says your x had to be e, okay? E is like about 2.7, all right? So the number line we're thinking about only has the 1 point on it for us to worry about. And so we're going to have to plug in something that's less. And 1 is the most convenient thing to put in there. And then something that's more. Gosh, I don't know. I'm just going to put in 3. The reason 1 is convenient is because the log of 1 is something that you know, right? But then the log of other numbers, probably not going to know off the top of your head. So we're going to come in here and find h prime of 1, not h of 1, but h prime of 1. 1 minus log of 1 divided by 1 squared. And so that log of 1 is 0. So we end up with just 1 out of this, which is positive. And now we test h prime of 3. So 1 minus log 3 over 3 squared. And I'm going to have to use a calculator to get that. 1 minus log 3 divided by 3 squared. I'm getting, oh, I don't have enough room to write it there. Sorry. I'll write it over here, about negative 0.011. Doesn't matter exactly what it is negative. That means this function was going up and then it switched to going down. So this tells us that x equals e is a local maximum. All right? Okay, great. All right, one more example. So this time we're classifying the critical points of p of x being cosine x plus sine squared x. Now, the reason why it says in 0 to 2 pi is because cosine and sine both have a period of 2 pi. Once you've found the critical points in 0 to 2 pi, you've really found them all, okay? Everything else will just be repetitions of that. So we will find p prime of x. The derivative of cosine is minus sine plus sine squared. This means you've got a chain rule problem. Something's being squared on the outside, so you'll have 2 times the thing that was being squared, the sine x, times now the derivative of that thing that was being squared. So that's going to be a cosine of x. All right. Now, if you spot there, sine will factor out of both of those, and you'll have a minus 1 plus 2 cosine of x. All right. Nowhere are we going to have those be undefined. Sine and cosine are super nice functions. However, we can have them be equal to 0. So we set this equal to 0. And when sine x is 0, you would have your x being equal to 0, pi, or 2 pi, right? And here, if this portion is 0, then that has to have your cosine x being 1/2. And then you have to figure out what the x values are for that. And those are going to be pi over 3. And I started to say 2 pi over 3, but that's just wrong. It's going to be 2 pi minus pi over 3. What is that? 5 pi over 3. Okay. So now we've got something that's a bit more convoluted because we've got these 5 different points in there. Yay. So I'm going to get my number line out here. My 0 and 2 pi going here on the 2 ends, and pi in the middle. Pi over 3 is pretty close to this end, and 5 pi over 3 is pretty close to this end. Okay. Now you want to use special angles because you want to be able to evaluate this stuff. So I'm going to choose pi over 4, pi over 2, 3 pi over 2, and let's see, 2 pi minus pi over 4, so that's 7 pi over 4. Okay, so our p prime of pi over 4, we'll plug back in there and figure out what's going on. And we will have the sine of pi over 4 is 1 over the square root of 2, and minus 1 plus 2 times the cosine is 1 over the square root of 2. So we have 1 over the square root of 2 times square root of 2, then minus 1, which is 1 minus 1 over the square root of 2. 1 over the square root of 2 is about 0.7, so this is going to be positive. Okay. Now we'll try p prime at pi over 2. Okay. Sine of pi over 2 is 1. And negative 1 plus 2 times the cosine of pi over 2 is 0. So we get negative 1. That's negative. So this says x equals pi over 3, because remember, between those two values, okay, it is a local, let's see, what was it doing? It was going up, and then it started going down. So this is going to be a local maximum, okay? And unfortunately, there just isn't enough room on this, on what I've got set up here. So I'm going to copy it and add another page in here. And we will finish this out. All right, so now we're going to think about deciding what is happening at pi. Okay, so we take our other test value here, the 3 pi over 2, and we get p prime of 3 pi over 2. We know we have to take the sine of 3 pi over 2, that's negative 1, times negative 1 plus 2 times the cosine of pi over 2 is 0. So we end up with a positive 1, that's greater than 0. And this tells us that x equals pi, because remember, we're concerned about the value that's between our two test values. So x equals pi is a local, and to see what's going on with that, you have to think about that it's going down and now it's going up. So that means that it's a local minimum, okay? All right, then I'm gonna take and copy this part, paste over here, and now we're going to check with p prime of 7 pi over 4. So the sine of 7 pi over 4 is negative 1 over the square root of 2 minus 1 plus 2 times the cosine of 7 pi over 4 is positive 1 over the square root of 2. So that's equal to negative 1 over the square root of 2 times negative 1 plus root 2, which is equal to 1 over the square root of 2 minus 1, which is going to be what, like negative 0.3. So it's going to be negative. So this tells me that x equals, well, which one was I looking at? The 5 pi over 3. So 5 pi over 3 is a local. We were going up. Now we're going down. Okay, so this is a local maximum. Okay. Then finally, we can take care of the x equals 0 and the x equals 2 pi at the same time. So if you notice here, we were going up to the right of 0 And before we got to 0, we would have had a copy of this. So it was going down here, and then it changed to going up. So we can say that x equals 0 and x equals 2 pi are local minima. Okay. You could think about those in the same way that we thought about the thing with the square roots, that it was at the edge of our domain, and therefore you only really needed to test it on one side. But then you have to think the increasing and decreasing, you know, what's going on with that. Okay. But in any case, this is what we essentially do with local max, local min. Okay. All right. I will see you all in class.